Okay, continuing on the differential equations, we will look today at slightly bigger and scarier cases to the ones that you have seen and suffered so much from in the workshop. Namely, we will look at second order linear ODEs and also at systems of ODEs. Now, the reason second order ones make an appearance is that they are ubiquitous in mechanics, hydrodynamics, and electrodynamics. Remember Newton's equations of motion, F equals ma, where a was the second derivative of the coordinate. Diffusion equations had second derivatives with respect to spatial location. Equations describing various oscillatory processes, second order in time. So what we will now need to look at are second order ordinary equations, and then a few lectures down the line from now, we will look at the partial differential equations that involve higher derivatives. Now, for lack of time, the lecture today will be rather thin on the proofs, but I will at least sketch the reasons why we are doing what we are doing. Now imagine we have an equation of the following type. So item 1, second order ODE. And we will only look at the linear ones. The most general case looks like something of this kind. d2f by d, for example, x squared plus some function p of x, df x plus some q of x, f of x equals some r of x. Well, this is second order because the highest derivative is second derivative. It is linear because all instances of the function f itself and its derivatives, they enter linearly. However, the three functions, p, q, and r, can vary between instances of the equations. And here, now I'd say the general task of solving this arbitrary p, q, and r would be a separate semester-long course. So what we will do today is we will only look at equations where p and q are not functions but constants, and where r is 0. So simplify down, because we only have one lecture for it, to d2f by dx squared plus a df by dx plus b f equals 0. Okay. Now, even this is pretty scary because the standard separation of variables trick is no longer applicable. Notice that we have second differentials and squares of differentials in the denominator, so we cannot actually just move all the x's and dx's to there and all the f's here and integrate because there are derivatives of different orders here. What we can do, however, is conjecture a form that the f might have by just the method of long and purposeful staring here. Let's think about a function that would satisfy such an equation. Let's look at the functions first that this entire operator leaves unchanged. So let us say we have d2 by dx squared plus a df by dx plus bf. Let's not have any f in here plus b, and we should f outside equals 0. Well, these are differential operators, and if we look really carefully at this, well, what is the function that such an operator would leave invariant? Right? So, for example, lambda, well, lambda in some cases is 0. Well, what is left invariant by the derivatives are exponentials. Right? Why don't we try? So, hypothetically, f equals e to the lambda of x. let's see what's going to happen if we substitute that there. We will have d2 by dx squared, then e to the lambda x plus a d by dx e to the lambda x plus b e to the lambda x equals 0. Okay, opening this up, we have lambda squared e lambda x plus a lambda e lambda x plus b e lambda x equals 0. Well, the real exponential for any finite values for lambda and x cannot actually be 0, so we can cancel it. Here, here, and here. So what we are then left with is lambda squared plus a lambda plus b equals 0. Well, actually, it's a quadratic equation for lambda. So we must have two solutions, lambda 1 and lambda 2, for which the right-hand side is going to be 0. So we've actually found situations where this operator guarantees us a 0 rather than something non-zero on the right-hand side, and that happens if lambda satisfies these conditions. So actually our attempt at postulating a solution has succeeded. We have found conditions under which an exponential is actually a solution. So let us first draft the process by which we are going to solve it, and then see a couple of equations using that process. So, first what we do is use a trial solution for form e to the lambda x. And this has to do with the fact that equations of this type have derivatives, and exponentials are known to be eigenfunctions of derivatives. So actually with a pretty high likelihood that is a solution. Then B, substitute in E lambda x in, get an equation for lambda, and then solve. So I'll take lambda 1 and lambda 2. Now let us also think about what happens when we take combinations of solutions. So this is our operator, and I'll call it omega. And I'll put a hat on top to signify an operator. So this entire equation should look like this. Omega operator f equals 0. Now, if we have found the lambdas of this kind, we know that omega e lambda 1x is 0, right? Because we have found lambdas such that it becomes 0. And then we also know that omega e lambda 2x is 0. Why don't we add these equations up with just some arbitrary coefficient? I'll multiply this equation by alpha and this by beta, and I'll add them up. We'll have alpha omega e lambda 1x plus beta omega e lambda 2x, still a 0. Now omega can be taken out of the bracket, it commutes with constant multipliers. So omega alpha e lambda 1x plus beta e lambda 2x is 0. So actually this is also the solution. Which tells us that if any particular function is a solution and any other function is a solution, then arbitrary linear combination is also a solution. So in fact, what we should look for is linear combinations of such exponentials. So see, the general solution is f of x equals alpha e lambda x plus beta e lambda 2x, where alpha and beta are indeterminate constants. Notice that we only had one such constant in the case of first order ODEs. Now that we have second order ODEs, there are two constants. So there will be 3 for third order and so on. So then D use initial or boundary conditions to find alpha and beta. Right, so initial conditions are when we know the function at some starting point or starting time, and boundary conditions when we know it at a couple of points in some interval, or we have any other information that would allow us to pinpoint these constants. So that then is a particular solution. And then check. So back substitute and check. Now, this only applies when the two lambdas are different. Now it is conceivable that they might be the same. Sometimes quadratic equations have two identical solutions. So there's a little postscript here, which I will not prove. That really is a long story. That if lambda 1 is equal to lambda 2, then the general solution is f x is alpha e lambda x plus beta x e lambda x. Notice the x in here. Now, quite why that should be the case is a very long story, but we will just make this remark here without proof. Okay, so we have a flow chart and a bit of explanation. This is not a rigorous derivation, this is not a proof, this is a sketch. Saying, okay, it looks like exponentials might be solutions for that. Let's just try an exponential. Okay, we tried an exponential, it works. Okay, let's bang them together with some indeterminate coefficients and hopefully find the coefficients. The principal, I guess, justification for this is if the result actually fits the differential equation, well, that's the answer. It doesn't matter how we got it. So for our purposes here, this is as rigorous as these things are. And realistically, get into time allocated. Okay, example. In your handout, there's a lovely equation. Y double prime minus 5 y prime plus 6y equals 0. Well, following the flow chart, so sub in e lambda x. So e lambda x double prime minus 5 e lambda x prime plus 6 e lambda x equals 0. Taking the second derivative there, lambda squared e lambda x minus 5 lambda e lambda x plus 6 e lambda x is 0. Cancelling the exponential because it never goes to 0. Lambda squared minus 5 lambda plus 6 equals 0. Now, I don't think anybody needs a reminder on how to solve quadratic equations, but some embarrassed smiles indicate that, well, maybe that wouldn't hurt. Discriminant b squared minus 4ac. So in this case, d is 25 minus 4 times 1 times 6, 1, and then lambda 1 is 5 plus 1 over 2, which is 3, and lambda 2 is 5 minus 1 over 2, which is 2. And these are our eigenvalues for that substitution that we made. In quantum mechanics, when you do such things, it's quite common to use the German word Ansatz. It's a trial function of some type that we substitute whilst we are looking for a solution. Okay, so we are here. We found lambda 1 and lambda 2, so it is time to assemble our general solution. Our y of x is alpha e 3x plus beta e 2x. We are also given an initial condition. We are told, as a starting problem, that y of 0 was 3 and y prime of 0 was 8. In the case where the independent variable is time, this would have corresponded to somebody measuring the initial coordinate and the initial velocity of our particle. Here, because the independent variable is x, this corresponds, for example, to initial altitude and initial slope of the ground, if we are dealing with y of x. So, substituting that in, we can say y of 0 is 3, so alpha plus beta must be 3. And then y prime, well, the derivative of this is 3 alpha times the exponential and 2 beta times the exponential. Exponential will become 1, so 3 alpha plus 2 beta equals 2. Standard system of linear equations. This all of you can definitely solve, so I will just skip the boring things here. This is 8. And that tells us that alpha is 1 and beta is 2. I think that works. And does it? What's the other way around? Alpha is 2 and beta is 1. This I think is going to work, so this is 6 and that is 2 and that is 8. And therefore our final solution, y of x is 2e 3x plus e 2x. And that hopefully corresponds to my handout, and it does. So the last thing to do, once again, is to back substitute and check. Now this can be perilous in itself, as you discovered in the workshop, where the checking ended up being longer than the solving. It is up to you, but I would still recommend that you do it. If you substitute that back into the equation and demonstrate that the result is 0, then you're done. Okay, so this is the case where the two eigenvalues were different. Let's consider the case when they are the same, where we have to use this so-called adjoint solution with the little x. For example, from your handout, and this is as a function of time, so f double prime of t plus or rather minus 4 f prime of t plus 4 f of t is 0. And we are given additional information that f of 0 was 1 and f prime of 0 equals 5. And that's what we have. Okay, so doing exactly the same now, but as a function of time, we assume that our solution has this on lambda t, and that whatever lambdas we find, then the general solution is a linear combination of the corresponding exponentials, because if two functions are solutions of a linear equation, then any of their linear combinations also exist. This, by the way, is true for Schrödinger's equation in quantum mechanics, which is why Schrödinger's cat exists. If a dead cat is a solution and an alive cat is a solution, then any linear combination of dead and alive cat is also a solution. And that weird situation is called Schrödinger's cat. So it's actually a consequence of this linear mathematics. Okay, subbing that in, we have lambda squared e lambda t, so that's the double prime, minus 4 lambda e lambda t plus 4 e lambda t equals 0. Cancelling the exponential, lambda squared minus 4 lambda plus 4 equals 0. Here it's immediately visible that this is lambda minus 2 squared equals 0. And that, of course, has two solutions, and both of them are the same. Lambda 1 is 2, and lambda 2 is 2. Now notice the subtlety. Here we have quietly generalized the quadratic equations in here. When you were doing that at school, you would have been told that this equation only has one solution, right? That it's equal to 2, and then that's it. And you would have been correct, right? There's only one unique solution here. However, in general, a polynomial equation of order n has n solutions, and here we are enforcing that. We're saying, no, it's not just one solution, it's two solutions that are identical. Okay, now that drops us into the postscript over there, and our trial, general solution must therefore be f of t is alpha e to the power 2t plus beta t e to the power 2t. Right, so we have x in there, but we have t here. Now, we use the initial and boundary condition again. So f of 0 equals 1 would mean that alpha e to the 2 times 0 plus beta times 0 times e to the 2 times 0 equals 1. And then f prime of 0 equals 5. We will have to be careful about differentiating that. So let's do the f prime separately. T is alpha times 2 e to t plus product rule beta e to t plus beta times 2 times t e to the 2t. And when we put the f prime to 0 here, we will have 2 alpha from here plus beta and plus 0 equals 5. Now, this is nice because alpha is equal to 1. That's immediately clear. Because the second term is 0, and then beta must be 3. And that matches my handout, and therefore our final function f of t is e to the power 2t plus 3t to the power 2t. There's a typo in your handout. Should be 2t. Let me just mark that for correction. Okay, and again, I strongly recommend that you substitute it into the original equation and demonstrate that that is in fact the case. Right. This is as far as we want to go on the second order ordinary. The next topic for today is something you've already seen multiple times when we considered chemical kinetics, and that is systems of ordinary differential equations. Now, in kinetics, because we are dealing with rate equations and the reaction rate is the first derivative of concentration, we will therefore be dealing here with systems of first order linear ODEs. Now, we are getting pretty deep into the corresponding mathematics in here, and if you open big mathematics textbooks, you will discover that actually by this point, very few things are solvable. If you have nonlinear differential equations, if you have differential equations with non-constant coefficients, things become pretty horrible. And that was actually a common pursuit in about the start of 19th century. Lagrange, Laplace, and the like were busy trying to solve as many horrible differential equations as they could, because classical mechanics and astronomy in particular offered ample opportunities for that. But for us, typically the policy these days is okay, it's either soluble analytically, in which case we do it if we have the patience, or if it's not soluble analytically, well, damn it, let's just dump it into a computer and solve it numerically. I'll teach you how to solve them numerically as well. I think I've already mentioned that in the Chemists 47 module. Anyway, item 2 is systems of linear first order ODEs with constant coefficients. We are looking at things like this. It's a system, and here I'll introduce notation that you maybe haven't come across before. It is a system in which the equations are numbered by an index k. So we have k different functions and k equations for them. So we have d, f, k, dt is a k1, f1 plus a k2, f2, and so on. So what this says is that that is for k equals 1, that's a11 f1 plus a12 f2 and so on. For k equals 2, that's df2 is a21 f1 plus a22 f2 and so on. We can write this out in matrix form as well. For example, for a 2 by 2 system, d by dt f1 of t and f2 of t will be the corresponding coefficients a11, a12, a21, a22, and then the same vector f1 of t, f2 of t. Now, these two forms for a 2 by 2 equation are equivalent. So if you multiply this vector by this matrix, you will see exactly such linear combination. Now, in atmospheric chemistry, it's not uncommon to see systems with hundreds of these things. If you look at how, for example, both polychlorinated or fluorinated hydrocarbons are transformed in the atmosphere and eventually destroy ozone and so on, those are huge systems of photochemical equations, which we now need to learn to solve. So of the great multitude of the things that occur in this area, we will be only looking at the equations that are first order, that have constant coefficients and don't have any free terms. So they're also uniform. Now, let us think about this. This has the general form like that. d by identity of some vector equals some matrix times the same vector. Now, I've already mentioned, I think, a couple of times when we dealt with kinetics, that such equations have a very neat general solution, but that solution is only computable on a machine. It's this, it's the exponential. It's e to the a t e over 0. In much the same way as we had it for scalars in the case of chemical kinetics, where this is so-called matrix exponential. Now, we can draw some inspiration from this. We can say, okay, this horribly general solution exists, but a numerical matrix exponential doesn't get us any closer to analytical understanding about what is going on. So, but what it does tell us is that the solution is in fact still a bunch of exponentials of numbers times perhaps some vectors. So what we will do is we will make the following ansatz. Right, so file solution of form some coefficient c times some vector v times e to the lambda t. So it is exactly, in fact, the same form as we had here in terms of time. It is something that depends on time exponentially, but because we now have a vector of unknown functions, we have a vector in front of this. Let's now substitute that in and look at what that is going to lead us to. We have a derivative in here, we have a matrix in here, and we have a lambda. So let us act with this derivative and act with this matrix and see what is going to happen. Now, on the left-hand side, we have a coefficient and d by dt of this vector e lambda t must be equal to this matrix A coefficient we can put in front, acting on this vector e lambda t. Let us take the derivative. The vector is time independent, so lambda pops out in front. The constant we can immediately cancel. We can just forget about it because it is just on either side. So in here we differentiate the exponential, and in there nothing happens. So we now have lambda v e to the lambda t is equal to a v e to the lambda t. Again, lambda t is never 0, so we can just cancel it. And what we then have is a v equals lambda v. Does that look familiar? This is eigenvector-eigenvalue relation. So actually what we need to do to find the necessary lambdas and the necessary v's that are going to give us a solution is to solve the eigenvector-eigenvalue problem for the matrix. So again, this is not a rigorous proof. This is a sketch at best, but this is how we solve those things. So let's make ourselves a plan and follow that plan. And we will now actually solve a very basic Newton's equations of motion. Equation of motion for a ball on a spring. Something that Newton could do around about 1650. But well, for 1650 that was seriously cool. 2020 this is undergraduate mathematics program. Okay, so first, if the system is non-uniform, try to make the system uniform. Make equations uniform by substitutions. whatever works, so that they are reduced into this general form. Second, we write in matrix vector notation. This is why I've been torturing you with that stuff. 3. Solve the eigensystem problem. For the matrix. And then your general solution is C1 V1 e to the lambda 1t plus C2 V2 e to the lambda 2t and so on, however many equations you have in the linear system, resulting in however many eigenvalues and eigenvectors. So then 5 use initial or boundary conditions. Find Ck and 6. Exactly the same caveat applies when your lambdas are equal. You would have to go to adjoint solutions, but again, in this course we don't have the time, so we will not see them in any problem sets or examinations. And let us follow this once and solve Newton's equation for a ball and spring. Well, you know that the equation is actually second order, but what we'll do is a fairly standard cheat in such cases. We will use coordinate and velocity as independent variables, which in truth they are. So F equals ma means F equals mdv by dt. So mdv by dt equals force. Well, what is the force on a spring? It's Hooke's law. So minus k x of t minus x of 0, where this is displacement from the equilibrium length of the spring, and that is the force constant of the spring. Pull it and it pulls back. Hence, it's a minus. And then the second equation is that dx by dt by definition is actually v. And that is our system. Now let us follow the first item here. That is, we need to first make it uniform, because it isn't. There's this x naught, that is the free term in here, kx naught. So let's make a substitution. Let us say that y of t is x of t minus x naught. What this tells us then is then dv by dt is minus k over m. I'll move m over here times y of t. And then dx by dt is exactly the same as dy by dt, because this doesn't survive differentiation. So dy by dt is v of t. Well, that's better because this is now uniform. Let us recast this into a matrix form. d by dt of v and y, v of t, y of t is some matrix v of t, y of t. Good. Now, what matrix is that? This multiplies y by that and v by 0. So that will be minus k over m, 0. This multiplies v by 1 and y by 0, 1, 0. That is our matrix. And that is this Newton's equation in the matrix form. Okay, we are now at item 3. Solve the eigensystem problem for that matrix. Now you know how to do it. I will not trundle painfully through the process. I will just write down the solutions. Lambda 1 and 2 are plus and minus k over m. And then the corresponding vectors 1 and 2 are the following: plus minus I root k over m, and then 1 here. Now we don't need to normalize these vectors because coefficients in front of them are arbitrary anyway. You can now see why people, when they deal with harmonic oscillators of this type, like to make this substitution. They say, okay, omega is root k over m. The people who did vibrational spectroscopy the second year will remember the reduced mass of the atomic system and the force constant of the bond that corresponds to the harmonic frequency in the end. That's actually the same volume as spring. So we will make that substitution, and that will replace quite a few things in here. So we will have lambda 1 and 2. It's now plus or minus omega, and then v1 and 2 is a vector that is plus or minus I omega, and then 1 here. Considerably easier. And then our original equations over there will have the square of that frequency over here because it will be k over m. Right, so our trial solution now is a combination of that. So we have v of t x y of t is equal to arbitrary coefficient 1, c1, vector 1 here. So that will be plus I omega 1, and then exponential 1. So it's e, what is it? And I missed an I in here. I omega. Plus I omega t plus c2 minus I omega 1, the other exponential, e minus I omega t. And that is the general solution. Now notice what is going to happen once we substitute in the initial conditions. So we can, for example, say that at time 0 we had no velocity, in which case these two coefficients will become equal. In which case what's going to happen is exactly what you saw in Euler's formulas. Remember what I told you about exponential functions, that cosine x was e to the I x plus e to the minus I x over 2. And sine was likewise with a minus over 2i. So notice what is going to happen if our C1 is equal to C2, like our initial condition would describe. We would have that and that, so we will have a difference in here. Sine x is e by x minus e minus x over 2i. So that minus this, so the numerator of the sign, then this I will be cancelled by this I in the denominator. In the numerator we will have a sine wave. In the denominator we will have 1 times that plus 1 times that. That is the numerator of the cosine. And so the velocity will act as a sine of time with frequency omega, and the coordinate will act as a cosine of time relative to the equilibrium position we have here. So, without going through the details of the initial and boundary conditions in here, actually the solution in this case is some arbitrary constant which is related to initial displacement, then times omega sine omega t. And in here we will have, let me take a look at cosine omega, which corresponds to your understanding of how a harmonic oscillator works. The coordinate goes as the cosine, and the velocity is the derivative of the coordinate. I think we need a minus in here as well to match up the signs. Okay, so the summary of the lecture. I have just about squeezed an absolute minimum of knowledge about how to solve second-order constant coefficient ODEs and systems of linear constant coefficients first-order ODEs. In both cases, you proceed by conjecturing a solution. It is exponentials. In the case of scalar equations, it's just exponentials. In the case of vector equations, these are exponentials times vectors. Substitute them in. In the case of scalar equations, you have a polynomial for lambda. In the case of vector equations, you have an eigensystem problem for lambda. Get those lambdas, get those vectors, put them back together again, find the coefficients from the initial and boundary conversion. So the procedure is boring and unpleasant, but absolutely necessary. We'll have practice with it in the workshops. Any questions?